Well, we are here starting a new chapter in 180, and that's the concept of chemical equilibrium. Okay, and it's a concept that we are going to use for the next several weeks. And before we get started with the chemical equilibrium, then there is a new concept that we need to develop, which is the dynamic equilibrium. And equilibrium, it's something you may relate that with something that is stable, like the figure that you see here, right? So as long as they don't move, they hold the position, or at least that's what it looks there. So if you cause too much disturbation there, then they might fall off from those rocks. So the concept of chemical equilibrium is in a way similar, but there is a little detail that we need to understand when it comes to dynamic equilibrium. So if we start reviewing how a chemical reaction proceeds, then based on what we study in chemical kinetics, then the rate of that reaction normally will depend on the concentration of your reactant. So the larger the concentration of the reactant, then the faster the reaction will occur. Okay, so in the normal course of a reaction, you consume your reactants and you make the products, right? That's the normal course of the reaction. And in terms of rates, instead of how fast the reaction goes, okay, so if you're consuming the reactants, then the concentration of the reactant will decrease, right? So reactants will decrease. And based on what we know of chemical kinetics, if you decrease the concentration of the reactants, then the reaction will slow down. Okay, so if it decreases, in this case the forward reaction, it's gonna make sense a little more in a minute, but the reaction rate decreases. You decrease the concentration of reactants, then the reaction will slow down. Now, this doesn't happen for every single reaction, but in certain occasions you will have that the reactants have the opportunity to combine together and regenerate the reactants. Okay, so as you start producing products, then they might react back to produce or to regenerate the reactants. Okay. Well, this assumes that you are not somehow removing the products before they have a chance to react. Okay, so if they are still in the container, let's say you have a sealed container, then the opportunity for the products to react and regenerate the reactants is possible. Now, we are still talking about the normal course of a reaction. During the normal course of the reaction, the concentration of the reactants will decrease, the concentration of the products will increase. So if you allow the products to regenerate the reactants, then what is happening during the reaction is that the concentration of the products will increase, and as such, the rate at which those products will regenerate the reactants then will increase. Okay, so this we can summarize as if the products are allowed to react to regenerate the reactants, then we call that reaction a reversible reaction, in which you have reactants going to products, and we call this the forward reaction. And then you have products going to reactants. Okay, I'm just writing that in the normal way that we see reactions, but what is happening is that the products are going back to reactants, and as such, well, it's like you are going in reverse, and therefore we call this the reverse reaction. So you will have your forward, let's say the forward reaction is your normal reaction. When you write a reaction, you are writing it in the forward direction. And therefore, those products, if they react back to produce or to regenerate the reactants, then that is the reverse reaction. But it's kind of impractical to separate those reactions as if they were two, because at least they are part of the same system. So it's not practical to write it like that. So we have a convention for those arrows. So normally, if you have a reaction that the products don't have a tendency to regenerate your products, is all of the reactants are consumed and you obtain only products at the end of the reaction, there is no reaction going back, then we use forward direction you call arrow. Okay, but when you have a reversible reaction in which the products can regenerate the reactants, then you use a double arrow. Okay, and these are called I think they are double harpoon arrows, but this is how we identify reactions that are reversible. And reactions that are reversible are subject to chemical equilibrium. Okay, so this arrow that you see here, this double arrow, is very, very typical for equilibrium reactions. And now the concept of dynamic equilibrium, because think about the presentation slide. You have those two rocks hanging from that branch on each side, and they were kind of static. So they were in equilibrium because they were holding their positions, and somehow the chemical equilibrium has to do with holding positions, but it doesn't have the meaning that we saw in that slide. That's more of a static equilibrium. If you move the rocks, probably they will fall off. But in chemical equilibrium is sort of a dynamic equilibrium. What does that mean? It means that those reactions are constantly happening. Okay? It's not that the reaction will stop at some point. I mean, it can. If the reaction goes to completion, then once the reactants are gone, then the reaction stops. In chemical equilibrium, there is no such a thing, because the forward reaction will continue to happen. Okay, just when you start, if you only have reactants, the forward reaction will start. That forward reaction will slow down with time, and the reverse reaction will start picking up. Because you are increasing the concentration of products. If you increase the concentration of products, that reverse reaction will, the reaction rate for the reverse reaction will increase. So this is what we are seeing here, right? So, but when it comes to dynamic equilibrium, so the concept is that those reactions will constantly happen. Now, the equilibrium comes from the fact that if you look at the concentration, okay, so in this reaction is H2 plus I2 that goes to 2HI. So these are the reactants, and the concentration of reactants will decrease, and this is the product, and the concentration of product will increase. Well, when you have an equilibrium reaction and you reach equilibrium, that means that the reaction will slow down at some point, and after a certain point, and this is when you reached equilibrium, then the concentrations stay the same. No change in the concentration of products, no change in the concentration of reactants. Okay, they are still reacting, so those reactants are still producing the product. A little redundant there, and the product is reacting back to regenerate the reactants, and that is happening constantly. The thing is, the rate at what those processes are happening is the same. Okay, so if we call rate of the forward and rate of the reverse, those rates are equal. Does that mean that the concentration of products and reactants are the same? Absolutely not. Okay, it just comes to the rate. Okay, so that is what we have here. Rate of the forward reaction is equal to the rate of the reverse reaction. That is the condition for equilibrium. The speed at which you are generating products is the same speed at what you are generating the reactants or regenerating the reactants. Okay? So I want to be very clear with this. So let me write that again. So the rate of the forward is equal to the rate of the reverse reaction. That has absolutely nothing to do with the concentrations. The concentration of reactant doesn't necessarily have to be equal to the concentration of products. Okay, remember, if you write the rates, there is a constant times the concentration of the particular reactant in that case. So the constant is dependent on the reaction. So it's something that is characteristic. Sometimes the concentration of the reactants could be larger, sometimes the concentration of the products could be larger. It depends. Okay? But the concept of dynamic equilibrium is that the rates are equal. Not the concentration, the rates. So that's the most important concept there. Okay? So here, after equilibrium, okay, so you may have a case in which the concentration of reactants it's much larger than the concentration of products. Let's call this case 1. And you can have case 2 in which the concentration of reactants is much smaller than the concentration of products. Okay, let's call this case 2. And you know what? There is everything in between. Can you have a system in which the concentrations are equal? Absolutely. Okay, but that's a characteristic of the system. You don't really have that much control about what is the concentration. You can, I'm going ahead of myself here, so I'm going to wait for that. So there is something that is controlling what case you have at hand. Is it a case in which the concentration of reactants is larger, or is it a case in which the concentration of the products is larger? So what controls what the concentrations are is the equilibrium constant. And for the next few weeks, or several weeks, I must say, all there is to what we're going to study here is about calculating equilibrium constants and using those equilibrium constants to determine concentrations at equilibrium for several different systems. Okay, so I hope you understand here that the equilibrium, when we are talking about chemical equilibrium, the concept of dynamic equilibrium is really important. Those reactions are not stopping, the reactions are constantly happening, but the speed at which those reactions, the forward and the reverse, the speed at what those reactions are happening is the same. What the concentration of reactants and what the concentration of products is going to be, that depends on the equilibrium constant. And that is material for a different video.